Ever since its discovery in the 16th century by Newton and Leibniz, calculus has become one of the most fundamental parts of modern mathematics, but many people still don't know what it is. So what is calculus, and why is it so important?
Before we jump into the core of calculus, we first need to give ourselves some background knowledge, namely relating to functions, gradients, and limits. Functions, by definition, are a set of inputs, called the domain, which have a set of corresponding outputs. For example, if I have a car that's travelling along a straight road for an hour, my domain is that hour. And for every time period during that hour, there will be a corresponding distance. After 10 minutes, the car might be 25 kilometers away. So when t equals 10, d equals 25. Gradients are a lot easier to understand. Put simply, they are the rise of a slope over its run. So, if I'm walking up a hill, and for every 2 meters I go forward, I go 1 meter up, it has a rise of 1 and a run of 2. So, it has a gradient of 1 over 2. Let's transfer this knowledge to the Cartesian plane. Let's have A at 3, 2, and B at 5, 7. The distance across between the 2 points is given by their x values subtracted from each other. Their distance in height is given by their y values subtracted from each other. So we're going to have a run of 5 minus 3, which is 2, and a height of 7 minus 2, which is 5. So if we apply the formula, rise over run, we're going to have 5 over 2 as the gradient. Now this can be expressed as a formula, where the coordinates of A are x and y, and the coordinates of B are x1 and y1. The gradient formula in this situation is y1 minus y over x1 minus x. Limits are the value something approaches but never quite reaches. For example, if we have 1 kilogram of a radioactive substance that halves in its weight every 100 years. After the first 100 years, there'll be half a kilogram of it. After the second 100 years, there'll be a quarter. After 300 years, there'll be an eighth, and so on and so on. And this value will continue to get smaller and smaller. It will approach zero, but no matter how long we wait, it will never actually reach zero. So we say it has a limit of zero. So, with this newfound knowledge, we can ask the question, what is calculus? The basis of calculus is to find the gradient of a single point on a curve. Prior to calculus, only approximations of the gradients of points of curves could be made, otherwise known as the secant. So, if we chose the point we wanted to find the gradient of, and a point very, very close to it, we could apply the gradient formula. How do you find the gradient of the exact point on a curve? Let's do an example with the curve y equals x squared, or y equals the function of x. So, the function of x equals x squared. The function of 1 equals 1 squared. The function of 2 equals 2 squared. So let's pick a point, x1. Or, if you like, x, fx. And we pick another point, which is the distance h across from the point x and x. Or, its x value is given by x plus h. And its y value is the function of x plus h. So the point is given by x plus h squared. So, we want to find the gradient of the line between these 2 points as h approaches 0. So if we remember the gradient formula, we can go y1 minus y over x1 minus x, or the function of x plus h minus the function of x over x plus h minus x as h tends towards 0. So we're going to have x plus h all squared minus x squared over x plus h minus x as h tends towards 0. Now this simplifies to become h outside of 2x plus h all over h, as h tends towards 0. But we can't sub 0 into this equation, because we're going to get something that divides by 0, and you can't divide anything by 0. So, what we do is we cancel the two h's, and something magical happens. We get the limit as h tends towards 0 of 2x plus h. This we can substitute 0 into, and we're left with the gradient is equal to 2x. So this means that at any point on the curve y equals x squared, the gradient is given by 2x. But what does this mean? Well, the gradient at any point of the curve describes the rate of change at that time. So, the derivative of the curve gives the rate of change. If we have a function that gives the displacement of a car, and we differentiate that function, we are left with a function that gives the velocity of the car. But the beauty of calculus is that it works both ways. As well as deriving a function, we can anti-differentiate it, or integrate it. So if I'm given the velocity of a car, I can integrate that velocity to find a function of the displacement of a car in terms of time. Now, when integrating, sometimes you do need a tiny bit more information, such as where the car was when it started. But the beauty of it is once you have this information, the amount of further results you can get is almost infinite.